ಪ್ರಿಯ ಸ್ನೇಹಿತರೆ, ಎಲ್ಲರಿಗೂ ಸಸ್ನೇಹ ಪ್ರಣಾಮಗಳು. ನಾನು ಯಶಾ KS, ಉಡುಪಿಯ ಕುಂಚಿಬೆಟ್ಟಿನಲ್ಲಿರುವಂತಹ ಶಾರದಾ ಪದವಿ ಪೂರ್ವ ಕಾಲೇಜಿನಲ್ಲಿ ರಸಾಯನಶಾಸ್ತ್ರದ ಉಪನ್ಯಾಸಕಿಯಾಗಿ ಕಾರ್ಯನಿರ್ವಹಿಸ್ತಾ ಇದ್ದೇನೆ. ನಾನು ನಿಮ್ಮ ಟೆಕ್ಸ್ಟ್ ಬುಕ್ನಲ್ಲಿ ಇರುವಂತಹ ಪಾರ್ಟ್ 2 ಭಾಗದ ಯೂನಿಟ್ 10 ಎಸ್ ಬ್ಲಾಕ್ ಎಲಿಮೆಂಟ್ಸ್ನ ನಿಮಗೆ ಟೀಚ್ ಮಾಡ್ತಾ ಇದ್ದೇನೆ. ಎಲ್ಲರಿಗೂ ಕೂಡ ಮತ್ತೊಮ್ಮೆ ಪ್ರಣಾಮಗಳನ್ನು ಸಲ್ಲಿಸ್ತಾ ಹಾಗೂ ಈ ಕಲಿಕೆಯು ಯೂಟ್ಯೂಬ್ ಮುಖಾಂತರ ಕಲಿತಿರುವಂತಹ ಈ ಕಲಿಕೆಯು ನಿಮಗೆ ಸುಲಭವಾಗಲಿ ಅಂತ ಹಾರೈಸ್ತಾ ನಾನು ಇಂದು ಎಸ್ ಬ್ಲಾಕ್ ಎಲಿಮೆಂಟ್ಸ್ನ ಪ್ರಾರಂಭಿಸ್ತಾ ಇದ್ದೇನೆ. Hello everyone. In periodic table chapter, we have already learned about S block elements. In that chapter, the group 1 and group 2 elements belongs to S block elements. So today, we will learn about S block elements. S block elements are those in which the last electron enters the s orbital. All of us know that the maximum number of electrons that can be accommodated in s orbital is 2. Therefore, group number 1 and group number 2 belongs to s block elements. So let us take the first group elements and even we can list out the elements belonging to first group. First group elements contains lithium, sodium, potassium, rubidium, cesium and francium. We call them as alkali metals. Why we are calling them as alkali metals? Because when they react with water, they form respective hydroxides. They are strong alkaline in nature. Now, let us take up the second group of the periodic table. The elements belonging to second group periodic table are beryllium, magnesium, calcium, strontium, barium and radium. We call them as alkaline earth metals. We call them as alkaline earth metals because they form oxides and hydroxides. Oxides and hydroxides are alkaline in nature. Not only that, the oxides of the alkaline earth metals they found in Earth's crust. So, its S block elements consists of first group periodic table called alkali metals and second group periodic table called as alkaline earth metals. So, alkaline earth metals and alkali metals together make S block elements. Now, let us learn in detail about the alkali metals only. First, I am taking up the occurrence of the alkali metals. Sodium and potassium are abundant in nature. lithium, rubidium and cesium are not that much abundance when compared to sodium and potassium. Whereas francium is a radioactive element. Its half-life period is 21 minutes. Let us take up the electronic configuration of the alkali metals. The general electronic configuration, I am representing the electronic configuration as EC. EC means electronic configuration. Noble gas NS1. So, general electronic configuration of the alkali metal is noble gas NS1. The outermost orbit contains only one electron. So, it readily loses its electron and forms M plus. Here, M denotes alkali metals. Therefore, they are highly electropositive in nature. So, let us learn the electronic configuration of lithium, sodium, potassium, rubidium, cesium and francium. The electronic configuration of group 1 elements you can see in table. Lithium atomic number is 3. Its electronic configuration is 1s2 2s1 or helium 2s1. Sodium, its atomic number 11, electronic configuration 1s2 2s2 2p6 3s1 or neon 3s1. Potassium, atomic number 19, its electronic configuration is 1s2 2s2 2p6 3s2 3p6 4s1 or argon 4s1. Rubidium, its atomic number 37, electronic configuration 1s2 2s2 2p6 3s2 3p6 3d10 4s2 4p6 5s1 or krypton 5s1. Cesium, electronic configuration 1s2 2s2 2p6 3s2 3p6 3d10 4s2 4p6 4d10 5s2 5p6 6s1 or xenon 6s1. Cesium atomic number is 55. Francium atomic number 87. Its electronic configuration 1s2 2s2 2p6 3s2 3p6 3d10 4s2 4p6 4d10 4f14 5s2 5p6 5d10 6s2 6p6 7s1 or radon 7s1. Atomic and ionic radii. As per the periodic trend for atomic size, alkali metal atoms are with the largest sizes in a given period. Alkali metal ions are smaller than their parent atoms. Atomic radii and ionic radii of alkali metals increase on moving down the group. Each atom is added with an addition shell contributing to the increases in size. Ionization enthalpy in alkali metals, because of the large size, the valence electron is loosely bound to the nucleus. Therefore, alkali metals have considerably low ionization enthalpy. The effective nuclear charge for all the elements of the group practically remains constant as the increase in the positive charge in the nucleus down the group is nullified by the increase in the number of screening electrons. Atomic size increases down the group and the attraction of the nucleus for the outermost electron decreases. As a result, ionization enthalpy decreases down the group. Hydration enthalpy. Hydration enthalpy of alkali metal ions decreases in the following order. Lithium ion is greater than sodium ion, is greater than potassium ion, is greater than rubidium ion, is greater than cesium ion. Down the group, the size of the ion increases, charge density decreases, and extent of hydration decreases. Because of the high degree of hydration, lithium salts mostly exist as hydrated salts. That is example LiCl.2H2O. Now, physical properties. All the alkali metals are silvery white, soft and light metals. Alkali metals have low density because of their large atomic size. Density increases down the group. Potassium is an exception with lower density than sodium. Alkali metals have low melting point and low boiling point. Alkali metals and their salts impart characteristic color to an oxidizing flame. Sodium is an alkali metal. So sodium, when it imparts to the flame, it gives golden yellow color flame to the sodium. Now I'm using sodium nitrite now. Sodium nitrates I have taken in a watch glass and a small amount of concentrated HCl is put into the sodium nitrite and I have made the paste. Now I am subjecting this paste for the flame test. Observe, it gives golden yellow color flame. So sodium gives golden yellow flame when it is subjected for the flame test. Now I have taken a potassium chloride. In the potassium chloride, potassium is present. So when I subject it for a flame test, it gives violet color or lilac color. So I have taken potassium chloride salt in the watch glass and added a small amount of concentrated HCl and I have made the paste. Then I am subjecting this salt to the flame test. Now observe the flame. Violet color or lilac color is observed. Alkali metals emit electrons when irradiated with light radiations. Therefore, cesium and potassium are used as electrodes in photoelectric cells. We have studied physical properties of the alkali metals. Now, let us move on to the chemical properties of the alkali metals. Alkali metals are highly reactive in nature because they have low ionization enthalpy. Now let us take up the alkali metal reacting with A. Here are the equations involved of the alkali metals reacting with A. Let us study these equations. When alkali metal reacts with oxygen, they form respective metal oxides. When these metal oxides hydroxide. When it is reacting with carbon dioxide, it forms respective carbonate and water will be formed. Here, in this equation, M denotes the alkali metals. Let us take up the examples. When lithium reacts with the oxygen, it forms lithium monoxide, Li2O. We call it as lithium monoxide. When sodium reacts with the oxygen, it forms sodium oxide, and also when sodium reacts with oxygen, it forms sodium peroxide. Na2O2 is sodium peroxide. Potassium, rubidium and cesium forms superoxide, and we can represent the formula as MO2, where M denotes the alkali metal. The second property, chemical property of the alkali metals, when alkali metals reacting with water, all the alkali metals react violently with water, their chemical reactivity increases from lithium to cesium. When they react with water, they form respective hydroxide and hydrogen is liberated. When we have taken the general equation for the alkali metal reacting with water, here is the equation. When alkali metal react with water, it forms respective metallic hydroxide and hydrogen is liberated. Let us take up one example. I have taken up sodium as the example. When sodium is reacting with water, it forms sodium hydroxide and hydrogen is liberated. So, when 2Na reacting with 2H2O, it forms 2NaOH, that is sodium hydroxide and hydrogen. Even though lithium has lowest electrode potential, it reacts less vigorously with water, because we have already studied that lithium is a small size and also it is having very high hydration energy. In the chemical properties of the alkali metals, next property is reaction with hydrogen. When all alkali metals, when they react with hydrogen at 673 kelvins, it forms respective hydrates. These respective hydrates are ionic salts. But lithium, when it is reacting with hydrogen, it reacts at 1073 kelvins. So one example I have taken, when sodium is reacting with hydrogen, it forms sodium hydride having the chemical formula NaH. Then next property, chemical property is when alkali metals reacting with halogens. We know about halogens. The group 17 elements are called as halogens: fluorine, chlorine, bromine, iodine. These we consider as halogens. And when the alkali metals reacts with the halogens, they form ionic solids. It is given as M plus and X minus. Here M is an alkali metal and X is halogen. Example I can give you: sodium chloride, sodium iodide, sodium bromide. In the same manner, chloride or lithium halides, I can say. Lithium halides are covalent in nature. The rest are ionic in nature, but lithium halides are covalent in nature because of the high polarizing capability of the lithium ion. In the chemical properties of the alkali metals, the next property is reducing nature. Alkali metals are strong reducing agents. Among alkali metals, lithium is the most powerful reducing agent because lithium has highest ionization energy and also lithium possesses electrode potential and that is the least in the lithium. Therefore, it is the strong reducing agent in the solutions. Lithium, strong reducing agent among alkali metals. The next chemical reaction of the alkali metal is solutions in liquid ammonia. When alkali metals dissolves in ammonia, it forms blue colored solutions. So, let us write the equation involved in that. The next property of the S block element among that alkali metal is solutions in liquid ammonia. Ammonia is NH3. When alkali metal, it is represented as M, X plus Y of the when it is dissolved in liquid ammonia, it forms M of NH3X plus ion and plus E of NH3Y minus. So they form blue colored solution. This blue colored solution is due to ammoniated electron which absorb energy in the visible region of light and thus impart blue color to the solution. These solutions are paramagnetic in nature and standing slowly and liberates hydrogen forming amide. So let us write the equation. This M plus and AM and representing that solution in ammonia. M plus AM represent solution ammonia, when it is reacting with the ammonia, means when it is standing for a long time, then it forms amide. Plus hydrogen gets liberated. In concentrated solution, this blue color that turns to bronze color, and this is diamagnetic in nature. Now let us take up the uses of the alkali metals. Uses of alkali metals. First one, we will take up the lithium. They form alloys with other elements. When lithium is reacting or mixed with lead, it forms white metal, and this white metal is used for bearings for motor engines. Lithium and aluminium forms an alloy, and it is used in aircraft parts. Lithium and magnesium forms an alloy. It forms armor plates, and this is used in thermonuclear reactions. And also, lithium is used in electrochemical cells. Next is sodium. Liquid sodium is used as a coolant in fast breeder nuclear reactors. Potassium plays a vital role in biological system. The compound potassium chloride is used as a fertilizer. Fertilizer means cobra. And also KOH, that is potassium hydroxide, is used in the manufacture of soft soaps. Soaps nalli potassium hydroxide na upayogistare. Potassium hydroxide is also used as absorbent for carbon dioxide. Cesium is used in devising photoelectric cells. General characteristics of the compounds of alkali metals. First one we will take up oxides and hydroxides. Alkali metals form monoxides, peroxides and superoxides. The stability of peroxide and superoxides increases with increasing size of metal ions. Peroxides and superoxides are bigger anions, and a stable, compact, close packing in the crystal structure is possible with relatively bigger metal ions. Smaller cations cannot have a compact, close packing with these ions. The oxides of alkali metals undergo hydrolysis with water, forming their hydroxides. The equations are as follows. M2O plus H2O gives 2MOH. M2O2 plus 2H2O gives 2MOH plus H2O2. 2MO2 plus 2H2O gives 2MOH plus H2O2 plus O2. Here, M is alkali metal. The oxides and peroxides are colorless compounds. Superoxides are yellow or orange in color. Superoxides are paramagnetic. Sodium peroxide Na2O2 is widely used as an oxidizing agent. The hydroxides of alkali metals are all white crystalline solids. They are the strongest of all bases and dissolves freely in water with the evolution of heat. Second characteristics of compounds of alkali metal, halides. The alkali metal halides, denoted as MX, where M is alkali metal, X is equal to F fluorine, Cl chlorine, Br bromine, I iodine, are colorless crystalline solids with high melting points. They can be prepared by the reaction of the appropriate oxides, hydroxide or carbonate with aqueous hydrohalic acid, denoted as HX. Alkali metal halides have high negative enthalpies of formation. The values becomes less negative as we go down the group for fluorides and more negative down the group for chlorides, bromides and iodides. The melting and boiling points always follow the trend. Fluoride is greater than chloride, is greater than bromides and greater than iodides. All these halides are soluble in water. Lithium fluoride is less soluble in water compared to other halides. This is because its lattice energy is very high as both the ions in lithium fluoride are small in size. The relatively lower stability of cesium iodide is due to smaller hydration enthalpy of its two ions. Other halides of lithium are soluble in ethanol, acetone and ethyl acetate. Lithium chloride is soluble in pyridine also. The third general characteristic of the compounds of alkali metal, that is salt of oxo acids. Oxo acids are those in which the acidic proton is on a hydroxyl group OH- with an oxo group attached to the same atom to which the hydroxyl group is attached. Example, carbonic acid H2CO3 is written as OCOH twice. Sulfuric acid H2SO4 is written as O2SOH twice. Alkali metals forms salts with all oxo acids. They are soluble in water. Their carbonates and hydrogen carbonate are stable to heat. Lithium carbonate is unstable to heat and dissociates into lithium monoxide and carbon dioxide. Lithium hydrogen carbonate does not exist as a solid. We have discussed about the physical properties and chemical properties of the alkali metals. Now, we will take up anomalous property of lithium. Anomalous behavior means unique property of the lithium. Lithium has small size and even in its ion also it is in small size. And lithium has high polarizing power, means charge by radius ratio. And lithium shows diagonal relationship to magnesium. Now let us take up the differences between the lithium and other alkali metals. Lithium is harder than other other alkali metals, its melting point and boiling point are higher than other alkali metals. Lithium is least reactive among the alkali metals, and lithium is the strongest reducing agent. Lithium forms lithium monoxide and lithium nitrite. Lithium crystallizes as hydrates. Lithium chloride dot 2H2O, and also other alkali metals do not form hydrates. Lithium bicarbonate is not obtained in the solid form. Lithium nitrate, when it is heated, it forms lithium monoxide, nitrogen dioxide and oxygen. When we balance this equation, it becomes 4LiNO3 lithium nitrate. On heating gives lithium monoxide and nitrogen dioxide and oxygen, whereas other alkali metal nitrates, on heating it gives respective nitrate. So let us take up one example. Sodium nitrate, on heating it gives NaNO2, sodium nitrite. And oxygen will be formed. When we balance this equation, it becomes 2NaNO3 becomes 2NaNO2 and O2. Lithium fluoride, that is LiF, and lithium monoxide, that is Li2O. It is less soluble in water than the corresponding compounds of other alkali metals. Now let us take up the similarities between lithium and magnesium. They have both lithium and magnesium. They have size, atomic size and ionic size are similar in nature. Example, lithium is 152 picometer, magnesium it is 160 picometer. If we take up lithium ions, then it is 76 picometer, and magnesium ion, that is 72 picometer. That is why they show the similar properties. Both are harder and also it is lighter, and both reacts with water, and their oxides and hydroxides are soluble in water, and lithium forms lithium nitrite, that is Li3M, and sodium forms magnesium nitrite, that is Mg3N2. Lithium oxide and magnesium oxide, when they react with excess of oxygen, they do not give superoxides. Carbonates of the lithium and magnesium decomposes easily on heating, and lithium chloride and magnesium chloride, both the salts are available as hydrates. Example, lithium chloride dihydrate, that is LiCl dot 2H2O, and magnesium chloride dot 8H2O. Some important compounds of sodium is that we are learning sodium carbonate. it is also called as washing soda. Its formula is sodium carbonate Na2CO3 dot 10H2 hydrated salt. It is manufactured usually by solvent process. The manufacture of sodium carbonate is as follows. When carbon dioxide is bubbled through brine solution and saturated with ammonia, it forms sodium bicarbonate. So let us write the equations involved in the Solvay's process. Ammonia NH3, when it is carbon dioxide is bubbled with brine solution, then it forms ammonium hydrogen carbonate. NH4HCO3 is ammonium hydrogen carbonate. This ammonium hydrogen carbonate, when it reacts with brine, that is sodium chloride solution, is called brine solution. It forms sodium bicarbonate, or even we can call it as NaHCO3 or sodium hydrogen carbonate and ammonium chloride NH4CO. Sodium bicarbonate or sodium hydrogen carbonate obtained in this step is precipitated, then filtered. Then sodium bicarbonate, on igniting, it gives out sodium carbonate. So sodium hydrogen carbonate, on igniting, it gives sodium carbonate Na2CO3 plus carbon dioxide and water. In this Solvay's process, ammonia is recovered. How it is recovered? When the solution is reacted with calcium hydroxide, then we get ammonia, then calcium chloride and water is divided. So ammonia is recovered by when the solution NH4Cl, it is reacted with calcium hydroxide CaOH twice. It gives ammonia, calcium chloride and water. So this is about the Solvay's process. What are the properties of the washing soda? They are white crystalline solid and its formula is sodium carbonate Na2CO3 dot 10H2. Sodium carbonate decahydrate loses its one molecule of water and forms sodium carbonate monohydrate. So let us write the equation for the sodium carbonate decahydrate losing the water molecule and forming sodium carbonate monohydrate. Sodium carbonate Na2CO3 dot NH2 at 373 kelvins. It forms sodium carbonate monohydrate. Monohydrate means containing one molecule of water. And 9H2O, it uses 9 molecules of the water. Sodium carbonate monohydrate H2. So above C 373 kelvins also we can write and forms sodium carbonate and water. What are the uses of the sodium carbonate decahydrate? Sodium carbonate decahydrate or nothing but washing soda, it can be used for the softening of the water and even in the cleaning process in the laundries, and it is used in the manufacture or preparation of the glass soap and borax. It is also used in the preparation of the paper, paints and also in the textile industry, and it is used as the laboratory reagent in the qualitative and quantitative analysis.